Hey guys, so today will hopefully be the start of a new series where I can kind of introduce the ins and outs, the design process for what has to be one of the first liquid fueled rocket engine programs, amateur liquid fueled rocket engine programs being developed currently in a high school. And yeah, so we'll just dive straight into it. Um, the topic for today's video is obviously the propellant combination. So how are you going to choose your propellant based on your mission, things like that. And one of the really useful pieces of software that you can use is called right here CEAgui. It stands for Chemical Equilibrium with Applications. It's open source NASA software. You can literally go to Glenn Research Center or whatever, and you can download their zip file. And I know for a fact that um, high high caliber propulsion courses like from Purdue Propulsion or USC Propulsion, they all use CEAgui. So it's a pretty standard program to use in the industry. Um, but basically, after you unzip their zip file, you're met with this, and basically to run it, you just click on this CEA win file, Windows Bash file, and just get started. And you get met with this Java GUI. And what you want to start with is just rocket, because it's a rocket problem. You can set your initial pressure, uh, which in our case would be 20 bar. You want to leave your combustion temperature at a sign because you want it to predict your combustion temperature. For the combustion chamber, this is really down to what you want to solve for. So you can do infinite area for the combustion chamber or finite area. I'm going to leave it at infinite area because I just want to know the kind of the theoretical maximum performance I can expect out of the engine and kind of work my way down from there. Equilibrium and frozen, those two don't really mean the same thing, but essentially equilibrium just means that when you're modeling combustion on I guess a simpler scale, equilibrium just means that you're assuming that the combustion process happens so fast that it completely combusts inside the combustion chamber, so then you can just take all those products and use the properties of those products to model your combustion throughout the nozzle. Frozen is the exact opposite. It's where basically the combustion is so slow that you take the reactants kind of, and you model their properties in the combustion reaction. Normally frozen will actually give you slightly, like I think it's 10%, around 10% an overestimate on your performance. So we're just gonna go ahead and uncheck equilibrium because we're just gonna go for frozen. Freezing point, yes, we want to freeze in the combustion chamber. And optional exit conditions, so PI divided by PE is just the initial pressure inside your combustion chamber divided by the exit pressure. And since we are designing a sea level engine, we'll probably move on to bigger engines later, but a sea level engine has a ambient pressure of 101,000 pascals, and converting that to bars, the initial pressure being 20 bars, I think that's around 19.38, I think. I'll have to check that later, but it's around 20. So we can just put that for now. Subsonic, supersonic, let's not worry about that. We just want to know the combustion properties. Click save, and next thing you want to choose is oxidizer fuel weight ratios. You can do any of these other stuff, but probably the most simple and most intuitive would be the oxidizer fuel ratios. And actually, we'd probably want to get to this later because you don't know your propellant combination yet. So you want to go over to this tab. So you want to go over to this tab called reactants, and this is where you can actually set your fuel and oxidizer. Just a quick rundown of some of the common rocket propellants, liquid fueled rocket propellants. By far the most common oxidizer is liquid oxygen. It's light, it's cryogenic, but it's still pretty accessible. It's not some of the other oxidizers, which are sometimes toxic or very corrosive. So we're just gonna go ahead and choose liquid oxygen. Amounts, that's the relative amount. So let's just set the scale to like 100. And then the temperature, I think it's around 90.19 Kelvin for around this boiling point. And for the fuel, we looked into a bunch of different fuels like hydrogen, methane, ethanol, RP1, and just kind of did the pros and cons of those fuel combinations. When it comes to it, the space shuttle uses hydrogen and liquid oxygen, but we're definitely not using hydrogen because even though it gives higher efficiencies, higher specific impulses, it's just the boiling point's like 20 Kelvin. It's way too cold for us to handle, so we're not using that. RP1 is pretty expensive because that's basically refined kerosene, and obviously you have to go through the entire refinement process, and that's a bunch of money. We can't afford that. Methane is becoming a good candidate, especially if you want to go to Mars, because you can synthesize methane on Mars, but it's currently still a kind of a new propellant combination with liquid oxygen, and I read up somewhere on AIAA that basically methane has some weird properties. It goes like supercritical when you're using it as a regenerative coolant, but we'll get more into cooling and some of the engineering later. But that basically led us to ethanol. Ethanol was first used by the Germans in World War II. But again, ethanol is hard to get your hands on because you can't just walk into a store and just, can I get very strong vodka? So what we're actually going to use is called isopropyl alcohol. I don't know why NASA has it under gaseous species. Maybe I'm just not good at chemistry, but it's somewhere in here. It's also called 2-propyl. 2-propanol, yeah, C3HAO, that's isopropyl alcohol. Whoops. Click OK. Relative amount. Now, normally isopropyl alcohol comes in 91% dilution, so we can actually do is put 91, because relative to the liquid oxygen, it's only 91. It's liquid at room temperature, so room temperature 298 Kelvin, and actually, because it's diluted, we actually have to select manually the whatever is diluting it, which is obviously water, so H2O as a liquid. 9, because 91 and 9 makes 100, and also 298. So now that you've made your reactants, you can press save, and now you can select your fuel to oxidizer ratios. If you're first researching the correct oil, if you're trying to get stoichiometric values for oxidizer to fuel ratios, basically what stoichiometric means is it goes through complete combustion. Like all the products cancel out to make reactants. You won't have any leftover reactants. Basically all of the fuel and oxidizer are used up. So that's stoichiometric, but sometimes you actually don't want stoichiometric because it's actually too hot, that to the point where it literally just melts your chamber. So if you're going through this the first time, you can kind of just play around with the values and see around where, for example, where like the optimal specific impulse kind of is, or what optimal temperature you want is. So I just put 1, 2, and 3 because that's kind of arbitrary for now. And once you've put that in, you're all set. You can click activity, execute. This dialog doesn't really matter. Keep pressing OK. And it takes a second. And there we go. So it just gives you this output file. It gives you all your inputs, and it gives you separate cases for your different oxidizer to fuel ratios, OF ratios. These are all the intermediate combustion products. So it's saying OF, oxidizer to fuel ratio, is 1. So 1. So here are the calculations, and these numbers are extremely useful. But what we're actually going to focus on for now is just the temperature in Kelvin in the chamber, about 2300 Kelvin, and ISP, which is specific impulse, it's around 1086. Let's just remember that, and actually, I have no idea why I only calculated one of the values. I think I didn't press save or something. Let's just go ahead and execute that again. That's odd. Well, I'll be back when I figured it out, I guess. So yeah, I have no idea why that happened, but basically I just redid the entire thing and turned it off and back on again, and it worked. So basically the values I put in is actually 1.0, 1.5, and 2.0 because I've done this before. I know around where I want it is 1.5, but I just wanted to kind of show you what the effects of the oxidizer fuel ratios are. So as you've seen before, 1.0 gives you 2300 Kelvin, 1087 ISP, and then you go to 1.5. Now it's computing for 1.5. You get much higher combustion temperature. This is closer to stoichiometric. You get a lot of more energy release, and you get a lot higher specific impulse. So that's good, but let's keep going. 2. Alright, well at 2 we have even higher and even higher. So we're seeing that it's still getting higher as we're increasing our oxidizer fuel ratio. So what you can actually do is just come back and you're like, okay, well, we know that 2.0 was good, but we can try going higher. Or in fact, you might kind of want to go 1.7 because you don't know which way it got better. Like, you don't know if the maximum is between 1.5 and 2 or if it's higher than 2. So we're just going to try this, and it's kind of a guess and check. I haven't really found a better way to do this. Hopefully it updates. Yes, okay. So 2.3, you can see that the specific impulse decreased even though the temperature is about the same. Now, when one of the let's say variables that contributes to specific impulse is obviously temperature. Higher temperature is better, but you also have to look at the molar mass of the products. You want lower molar mass, which means you want lighter products, because that means that you're basically getting, again, this is kind of a technicality, kind of broken down. It's not the complete explanation, but basically you have lighter products means higher exhaust velocities, which is better. So that's why you can see that in 2, when we had 2, the M here was 24. You come down here and it is around 25. So that increase actually negates the relatively similar combustion temperatures, so that it brings down the ISP to around 1097, while 2.0 is 1121. Let's check that 1.7. Oh, well, 1143. So it seems like it is between 1.5 and 2. So 2.3 is going too far in that direction. So let's just check on both sides of 1.7 and see which side is better. So we can try 1.6, 1.7. Let's just do 1.8 and 1.9. So we don't have to do this a bunch of times. Save it, execute. 1.9. 1128, 1.8, 1136, that's better. 1.7, 1143, so that's even better. 1.6, 1149. So it seems like 1.6 is the best. So by best, I mean the specific impulse is the best, but again, depending on your mission, depending on your budget, depending on a lot of different factors, you might actually not want to use 1.7. So 1.6. Oh, well, I guess 1.6 is the best. Yeah, my bad. So 1.6, yes, 1.6 seems to give you the best specific impulse. Am I? Yeah. 1.6 gives you the best specific impulse. So you see that the temperature is 3245. Down here is 3284. So that's actually kind of good because your temperature it's still very high. It's still over 3000 Kelvin, but at least it's not like even higher, you know? So this is good because that means that our optimal specific impulse I mean, it's still really high combustion temperature. So the kind of decisions you need to make when you're deciding on your oxidizer fuel ratio is, can we handle this temperature? And in the case of graphite, which has like a melting point of like 4000, yeah, it's really not a problem that we have 3000 Kelvin. But if you want your engines to be reusable, if you want to be SpaceX, if you want to be Rocket Lab, well, not Rocket Lab, but if you want to have a reusable, if you want to have any sort of economical merit to your rocket design, and you want to use, for example, regenerative cooling so that you basically don't have to throw away your engine every single time with graphite, because graphite's ablative. That just means the way that it cools itself is basically the top layer of atoms basically just gets slowly shedded away. That's why it transfers the heat away from the surface, so that's why it can handle such high temperatures. But the downside, of course, is you want your nozzle and your chamber to be optimally shaped. So if the shape is constantly changing because you have graphite, then you can't use it more than once because the geometry is just worn away. So yeah, now that you have your data here, we're just going to keep that there. And actually here in Project Caelus, which is our project name basically, here at Project Caelus we've developed just a code of Python, simple Python code, input outputs, that sort of thing, and it's basically based off of a bunch of equations that we found in Rocket Propulsion Elements 9th edition by George Sutton and Oscar Biblars, I think. It's basically a rocketry textbook. It goes through nozzle theory very thoroughly. I highly recommend it. The reason I read it was actually because I read up somewhere that Elon Musk had read it, and also some of my friends in college recommended it as well. So yeah, we based our equations off of that. We wrote it into a code so we don't have to plug it into the calculator every single time. And we just called it nozzlecalc.py. So if you want to execute it, Python nozzlecalc.py. So it asks for a bunch of things that we want. So our current engine design is 2 kilonewtons. The chamber pressure is 2 million pascals. Ambient temperature is sea level 101,325. Oxidizer fuel ratio, we saw that our oxidizer fuel ratio is 1.6. So let's go ahead and put that in, 1.6. What's the chamber temperature is 3,245.13. Gas molecular mass, that's just the capital M, 1 divided by N. That's 22.332. 22.32. 332. Ratio of specific heats, that's also known as gamma. So here you see the gammas, and gammas are dynamic. You can see that it changes as the gas goes from chamber, throat, and exit, but generally you just want to use the chamber because that's your starting value. 1.2029. Characteristic chamber length. Now, normally, this is just a characteristic that kind of defines the volume of your combustion chamber. Like, how big does it have to be to achieve complete mixing and combustion? And normally this is just a function of the propellant combination itself. So you just kind of have to Google it. You can search on some databases. I personally got mine from Rocket Propulsion Elements, and for all intensive purposes, unless you're using like ethanol, hydrocarbons like methane, propanol, propane, the isopropyl alcohol, most of these hydrocarbons with LOX have a characteristic chamber length of 1.0. You might want a bit more because ethanol has kind of an unusually large chamber length. It's not really a length, it's just, it is a length just because of the units, but it should think of it as a scale factor for the volume of your chamber. Ethanol has to go up to like 1.5 or to 2, but right now we just need 1.0. We hit enter, and just nicely inputs, outputs, nozzle dimensions as well. We can see that our specific impulse is 242 seconds. Calculates throat temperature, exit velocity, flow rates we'll need, exit temperature, exit Mach number, pressure ratio, expansion ratio, and these are all the nozzle dimensions. So this is very useful. Again, this code is completely based off of the kind of equations you find in the book I've mentioned. I'll leave a link in the description. It's very useful, and now that we have our dimensions, I think this is a good stopping point for this video. Thanks so much for watching, and I'll see you in the next one.